Okay, hi everyone. My name is Rösler, and the paper that I present today has the title Systematization of Knowledge for Game-Based Security Models of Group Key Exchange. And this is joint work together with Bertram Pöttering, Jörg Schwenk, and Douglas Stabila. And we directly start with the core of our paper, which is the idea of group key exchange. And we can motivate group key exchange easily by the most recent and most prominent use case, which is group messaging. So we can think of group messaging being split in modern applications into a first group key exchange phase where the members of a group exchange a key. And then this key is used to encrypt every group message exactly only once, instead of encrypting every message multiple times individually to all the receivers in the group, which is, for example, done in Signal. Now, we look only at the key exchange component here, so multiple users exchange a key, possibly in dynamic groups. So maybe users are added to the group, and these users can then exchange new keys with the new member set. Maybe users are added simultaneously, and eventually all the users compute in a group the same shared group key. But we are looking at the security of group key exchange, which means that we also have to consider adversaries that can maybe reveal key material or that can introduce and add malicious users and control the traffic between all the members while exchanging the keys. And the ultimate goal against such an adversary is, of course, that the keys are secure, meaning that they look random to the adversary, even though they are exchanged between these users. And now when we look at the literature of group key exchange, we see that there are many, even hundreds of papers on this topic. Specifically, if we look at the DBLP paper repository, we see that there are more than 150 papers with the title Group Key Exchange or Group Key Agreement. And we can split this literature into three different phases. The first one started in the early 80s, where researchers proposed new protocols for group key exchange, but they only provided heuristic security arguments instead of rigorous security proofs. And these rigorous security proofs were only introduced in the second phase, which roughly started in the early 2000s, leading to the final current phase on group key exchange research, where researchers try to understand which properties are relevant and important for the specific use case that I mentioned earlier, which is group messaging. For example, asynchronicity is one of the properties relevant right now. And since our main core consideration is the modeling and the definition of security for group key exchange, we ignore the rather vague and not really rigorous security analyses from our consideration, but still we see that there are more than 30 different definitions of security for group key exchange in the latter two phases of research. And this brings us to the core question and problem that we investigate in our paper here, which is systematization and unifying the ideas and security definitions for group key exchange. Now, with this goal in mind, we have to understand what is group key exchange, what are the generic definitions of it, and how can we define security for it. And for this, in the literature of key exchange or in the literature of any cryptography, we first of all start with syntax, which describes the abstract interfaces that capture the inputs and outputs of group key exchange algorithms in general. And for this, we look at one user here in this picture, and this user, as well as all other users, run on their local devices the group key exchange algorithms. And these algorithms have, of course, interfaces to their environments. For example, to the upper layer application. We have to keep in mind that group key exchange is never a standalone application, but always serves with the exchanged group keys to a application that uses these keys. But this application, in addition to obtaining these keys, also wants to control the group key exchange algorithms by, for example, changing the member set and many other things. There are also other interfaces, like the network interfaces, that helps these algorithms to communicate the information necessary to exchange keys between all the members of a group. Also, the storage interface for saving key material for these algorithms on the local devices are important. Now, there are different properties that these abstract interfaces have to fulfill. The first one being that these interfaces have to help the algorithms to become useful, such that the environment can use these algorithms for their different purposes. For example, sending the ciphertext or exchanging keys for the upper layer application. The second property being that these interfaces should be defined as generic as possible, such that different constructions can be captured by this framework. This helps us on the one hand to compare different types of constructions in the same framework. It helps us on the other hand, in practice, if a group key exchange is deployed along an application, that this group key exchange construction can be replaced by another construction if the former turns out to be insecure. And lastly, the property is that we want that these interfaces are as little restrictive as possible, such the construction that implement these interfaces can be very efficient and can also be as functional as possible. Now, turning to the security perspective, we have to look at which security goals do we want to be fulfilled and which types of adversaries do we want to capture. So in the presence of these adversaries, a good idea for defining security is that the security goal is defined intuitive. And one type of security definition could be that the keys look random to everyone except for the designated members, specifically for the adversary. On the other hand, we have to capture adversaries as realistically as possible. For example, an adversary should be able to control the interfaces, specifically the public inputs, controlling the member set, controlling also the communication of the algorithms via the network, and also probably corrupt the secrets that are stored on the local devices, at least temporarily. Okay, so these are the overall ideas that we think have to be considered when defining and modeling the security of group key exchange. And now what we did was looking at the literature that I introduced at the very beginning, but we saw that there is a very large literature, so we reduced the considered papers based on the properties that on the one hand, we only considered papers that appeared at Tier 1 conferences, and on the other hand, we considered papers that did not appear on Tier 1 conferences, but contributed new insights to the modeling of group key exchange, which resulted in a set of 12 different papers. Now, for these 12 different papers, we defined a framework with which we characterized the different types of definitions that we see when modeling group key exchange. You see here the characteristics that we think are relevant when defining the syntax for group key exchange. And with this framework, we then analyzed how the different papers implemented these characteristics or features of the syntax. And we also try to understand what we think are desirable implementations of all these features. We continue to do this for the security definition, for the partnering or matching definitions, and also for the correctness definitions. And the result of our analysis was that none of the papers that we looked at provided a generic standard model for group key exchange. And we can also say this for the papers that we did not look at in the very details that we looked at for the 12 papers that we consider in our systematization. The reasons for this are, on the one hand, that many of the definitions are too informal or underspecific, because the definitions are not clear enough to understand what exactly the requirements are that are captured in those. Secondly, we saw that many of the models are overfitted, meaning that many of these models were designed for the analysis of one specific construction, and thereby these models are not applicable to other constructions and cannot be generalized appropriately. Lastly, the shortcomings are that many of the external environment properties or requirements were ignored in the literature before. For example, many of these models required that a public key infrastructure is deployed along these group key exchange constructions, or many of the models did not allow us to generically compose group key exchange according to these models with other upper layer applications. So our result was that we came up with a new model, and you may now ask that this is just yet another model, and we think no, it is a good model because we learned from the past, we concentrated on what modeling should fulfill, and we rethought what group key exchange in general is. So we came up with a new syntax definition and security definition that is both precise and compact. Because we are independent of previous constructions and we give a compact pseudocode game definitions both for correctness and security. Along other properties, our model is indifferent to membership operations. So we fulfill, or we can capture, many different types of constructions. The ultimate result of our model is that we can handle different real-world settings within one model framework. On the one hand, we can capture asynchronous communication. We can consider different means of authentication for the group key exchange constructions, and our model is easily extendable and, as I mentioned, compact and precise. So you see here my overall agenda, or the overall contributions that we provided. On the one hand, developing a new and fresh understanding of what group key exchange is, then deriving from this understanding a systematization framework with which we then compared and analyzed the literature, basically the models that were proposed in the literature. And we came up at the end with a new generic compact model with which we think we can help the future research on group key exchange to understand what the basic properties for a group key exchange model should be. All the details are in our ePrint publication, and you can contact me via Twitter. I thank you very much for your attention. Thank you very much.
I'm Jacques Traoré, and I will present the results of our paper entitled EPID with Malicious Revocation. In this paper, we revisit the security model of an anonymous signature schemes called EPID, which has been introduced by Brickell and Lee in 2007. This is a joint work with Olivier Sanders. Enhanced Privacy ID, EPID for short, is a digital signature scheme supporting anonymity. Just like a group signatures, an EPID signature attests that a legitimate signer belonging to an identified group of signers generated it. By group, we mean here, for example, a group of eligible voters who are allowed to participate to a given elections, or a group of customers who subscribe to the services of a given service provider. Anyone can check the validity of an EPID signature using a so-called group public key. EPID signatures are anonymous. We don't know who among the group of signers generated this signature. And contrarily to group signatures, they are untraceable. That is, no one can open an EPID signature and identify a signer. An EPID private signing keys can, however, be revoked given a signature created by that key. EPID is standardized. It is included in the ISO standard 20008-2 on anonymous digital signatures. EPID is widely deployed. It is embedded in billions of devices, as disclosed by Intel during the RSAC conference in 2016. Three types of entities are involved in an EPID scheme: an issuer, the member of the group or the signers, and verifiers. The role of the issuer is to manage the group of signers, and to issue to legitimate member his private signing key. With his private signing key, a member can sign any message on behalf of the group. And anyone, any verifiers, can verify the validity of his signatures using a group public key published by the issuer. How does it work in practice? So in the joint protocol, the member will have to choose a secret S, which will be his private key, and then execute with the issuer a blind signature protocol in order to obtain a blind certificate on his secret S. To sign a message M, he just has to compute a non-interactive zero-knowledge proof, proving that he knows a secret S that is being certified by the issuer. And the verifier can verify the validity of this non-interactive zero-knowledge proof by using the group public key. A private signing key can be revoked using a signature that has been generated with that key. So to this end, the member just has to add to his signatures a revocation tag that can be computed as follows. So he just has to choose a random value H and compute the revocation tag, which is equal to H to the power S, his private signing key. Before signing a message, he just has to retrieve the signatures revocation list, which contains revocation tags of all revoked signatures. To sign a message, he then has to compute a non-interactive zero-knowledge proof of proving that he knows S and a blind certificate on S, a proof that the revocation tag has been correctly computed, that is, that T is equal to H to the power S, his private signing key, and that he did not produce any of the revocation tag, RTI, including in the signatures revocation list. So he has to add a proof of knowledge that TI is different from HI to the power S. From a security point of view, EPID signatures should be unforgeable, which means that an adversary should not be able to forge a signature either by framing an honest user that is signing on behalf of this honest user, or by using forged key, that is, keys that have not been obtained during a joint session. So in practice, obviously, I may corrupt users and then own their private keys. So how to detect in this case that a forgery is non-trivial? That is, that this signature has not been generated using a corrupt key. A solution to this issue would be to recover all the corrupt keys owned by the adversary. In current EPID constructions, this is done by requiring a zero-knowledge proof of the secret S during joint session. This has two main drawbacks. The first one, if we use classical rewinding techniques to extract as corrupt keys, this will limit the number of concurrent joint sessions that can be done securely. On the other hand, if we use online extractor, this will negatively impact the performance of the joint protocol. An EPID scheme should provide perfect anonymity to the signers, provided obviously that their private signing keys are not revoked. A natural question that comes to mind is who should manage the signatures revocation list? In current security models and EPID constructions, it is assumed that this revocation list is managed, that is signed by a trusting entity. So this would lead to a centralized and not very practical solutions. So it would be more convenient for the verifier if they could manage themselves this revocation list. We should also emphasize that in the ISO standards, it is only recommended to have a trusted entity for updating the signatures revocation list. It is not a requirement. So another natural question that comes to mind is what can be achieved in terms of security if this revocation list are generated by a malicious entity. We observe that if such a revocation list is managed by a malicious entity, this entity could easily win the current anonymity games by simply adding to the revocation list randomized versions of the revocation tags instead of the original revocation tag. So we revisit the security model of EPID by removing some limitations of previous words. We propose a new unforgeability game where this time we ask the adversary to produce n+1 valid signatures if it owns n corrupt keys that have been obtained during successful joint sessions. We, however, put in the revocation list each new signature that it produces in order to ensure that the n+1 output signatures were generated with n+1 distinct keys, which means that at least one of these output signatures is a non-trivial forgery. So we do not require to recover all the corrupt keys. We also proposed a new anonymity game where this time we give to the adversary a total control on the revocation list. We also propose two new EPID schemes that satisfy our new security and functional requirements. In both constructions, we modify the structure of the revocation tags. In our constructions, they are non-malleables in order to prevent their randomizations and to prevent the attacks that I just mentioned in one of my previous slides. So to summarize, EPID is a standardized anonymous signature scheme which is widely deployed. It is embedded in billions of chips. We have proposed a new security model for EPID which addresses several limitations of previous models. Our new unforgeability property removes the need to extract corrupt signing keys, which will make enrollment of new members simpler and which will allow concurrent joins. Our new anonymity property allows a decentralized management of revocation lists, which we believe better captures the spirits of EPID. Finally, we have introduced two new efficient EPID schemes that satisfy this new security and functional requirements. Thank you.
Hi, my name is Magnus Ringerud. I'm a Ph.D. student at the Norwegian University of Science and Technology, and I'll be talking about our paper, Signed Diffie-Hellman Key Exchange with Tight Security. This is joint work with Jacques and Chen Jia, also here at the university. So a brief outline of this talk. I'll give an introduction and try to establish some context for our work. Then I'll move into some technical aspects and finally some real-world relevance, as in why is this important for you. So to start off, we have to mention the TLS, the Transport Layer Security. TLS is used everywhere, and it is dependent on a key exchange algorithm for establishing shared key material. And when I say everywhere, in particular, it's used as the security layer in HTTPS, which is used on the RSA conference webpage. Now, signed Diffie-Hellman is a core part of TLS and is one of the algorithms used in this handshake, where you have two players, Alice and Bob, which is trying to create shared key material. And there are many variants of signed Diffie-Hellman. The point is you have a Diffie-Hellman share and you sign it to get authentication and integrity. So this is our version of the protocol, where we at the end have this context where you have the public keys and you have both the messages, and then you hash this together with the shared keying material, which is this y to the x term and x to the y term. You hash all this to get the final key. And this is important, and we'll get into it later. So previously, the previous security bound for signed Diffie-Hellman was made by Rösler and Jacques in 2018. And as you can see from the equation, it's dependent on breaking the decisional Diffie-Hellman problem and the multi-use security of a digital signature scheme. The important part here is this S squared term. Now, S is the number of sessions, and hence we say that this is a security loss that is quadratic in the number of sessions, so S squared. And now I mentioned security loss, and that brings us to tightness. Why is tightness important? Well, security loss reduces the guaranteed security level that security proof gives you. And a naive proof, or an easy proofs for signed Diffie-Hellman and many authenticated key exchanges, have this S square security loss. And what this means in practice, you can consider a case where S is 2 to the 30. Then according to such a naive proof, if you implement for 128-bit security, then in reality, you only obtain 68 bits of security. This is not a safe margin for large-scale applications. So our contribution is then a tight reduction to the strong computational Diffie-Hellman assumption. So we get rid of the security loss, and we abstract ideas from recent tight proofs for the TLS protocol. So to mention state-of-the-art for tightly secure AKE, or AKE in general, there are variants of signed Diffie-Hellman which has been proposed, but most lose this factor of S squared. There was a 3-message variant proposed by Rösler and Jacques in 2018, but this is, since it's a 3-message, it's not back and forth, but it's that way, and that way again. So it's an additional message, which of course increases the communication complexity. It is also proven in the multi-bit model, which does not automatically give you a tight composition with symmetric primitives like AES, which is what you want for TLS. There was also a recent tight secure AKE by Jacques, Kilt, Riepel, and Schage, which used some more sophisticated techniques to obtain tightness, which ours is very simple and straightforward, and the protocol is very well known. So, some technical details. This is a sketch of the model, and it's going to be very simplified, but it'll suit our purpose. So the idea is that you have an initiator which generates a message and an internal state. It sends the message over, and then you have a responder who generates his response message. And now, since he has all the necessary details, he can also compute his key. He then sends the response message back, and the initiator computes, hopefully, the same key. Now, the idea here is that the adversary can learn these messages and transcripts, as we call them. And in our very simplified model, we can say that the adversary wants to be able to compute a key. In the real model, it's a bit more sophisticated, but the easy model will suffice for our purpose. So why is tightness for AKE hard? Well, we have this thing called the commitment problem. And a reduction or security proof is just a way to relate mathematical problems or a scheme to another scheme. And then you have a challenger, you have a reduction, and you have your adversary. And the reduction wants to use the adversary to solve the challenge. That means that you need to embed your challenge in some way. If you don't, then you could just attack the scheme without using the adversary at all, and you have a more of a direct proof than a reduction in some sense. But this brings about a problem, because if you embed the challenge everywhere, you're not able to compute everything anymore. And in particular, for AKE, you have to be able to respond to what's called a key reveal query, which is a model of what happens if a session key is leaked, somebody gets hacked. You need to be able to model this and then make sure that the protocol doesn't break down. But you can't answer this unless if you can't compute the relevant keys. So this is a problem if you want to just use the naive way. So embedding it everywhere doesn't work, but simply guessing which sessions are important and trying to embed them there means that you have to guess correctly twice out of S times, which gives you this S squared loss. So the naive solution leads to highly non-tight proofs. So our approach is then this random oracle, because instead of actually computing this y2x, x2y term, you simply simulate the random oracle and then you patch them later on. This means that you can now, in a consistent way, answer these key reveal queries. So everything seems good, but there's then still one challenge remaining, and that is that since we are in the random oracle model, the adversary can also query the random oracle itself. And if he happens to query on this particular context and then with some element appended at the end, we need to be able to distinguish, is this element the key that you would compute from this context, or is it just random? And the answer to that should determine if he gets what the response from the random oracle is the actual key or just something random. So in short, we need to be able to distinguish, is this element a key that you would compute from a context or something random? And then our solution is then what we call verifiable key exchange. So you have a key exchange protocol, but you also have a verification oracle that can verify with a given transcript and a key if this key matches this transcript. And for signed Diffie-Hellman, we use the oracle provided by the strong computational Diffie-Hellman assumption. So how does this affect you? And good news, our analysis supports the current implementations based on this strong CDH assumption. So most implementations today simply ignore security loss and implement everything as if it were tight. And our analysis supports that these implementations should still be secure, which is good news if you're able to have a slightly stronger assumption. And then you have the model and performance table. So we compare with some of these other AKEs I've mentioned. This table is obtained with a tightly secure multi-user signature scheme. So all the schemes get the same amount of extra group elements, etc. So we are communication efficient and we are in the correct single bit model in our proof. One drawback to our work is that we do not allow state reveals like this JKRS work does. However, TLS itself does not allow state reveals either. One of the reasons is that when you use signature schemes, they are in general not resistant to state reveals. Like Schnorr, for instance, if the secret state leaks, then your signing key is open for grabs, which is bad. So to conclude, we have a tight reduction for signed Diffie-Hellman Key Exchange, where we have improved the security loss from this S squared to a constant, so 1. And this then extends to TLS because signed Diffie-Hellman is one of the core components of TLS. We have a new key technique, which is verifiable key exchange, which is an abstraction of many tight security proofs who use different kinds of oracles to respond exactly as we would, especially this last one here marked with a star. This protocol is not entirely tight, but it is they use exactly the same oracle simulation as us, so it seems fitting to include it here. And finally, the extension of this, or our ongoing work, is to extend this to group key exchange. So we want to have group key exchange with tight security through this verifiable key exchange. And that is my talk. Thank you for listening.